Hello, my name is Aina Najwa binti Morni. My matrix number is CD240149. Today I'll explain the theory behind the thin cylinder experiment, which help us understand how cylindrical structures like pipelines, pressure vessel, and aircraft part behave under pressure. What is a thin cylinder? A thin cylinder has a wall much thinner than its diameter. When subjected to internal pressure, it experiences three types of stress. First, Hopf stress, which acts around the cylinder circumference, trying to burst it. Second, axial stress, which stretches or compresses it along its length. Last and third, radial stress, which acts through the thickness but is so small it usually ignored. Deformation and behavior. These stresses cause deformation, such as changes in the diameter or length. If the stress stays within the elastic limit, the cylinder returns to its original shape. Beyond this limit, the deformation becomes permanent. Why it matters? This experiment is crucial for ensuring the safety of structures like storage tanks and pipelines. It validates design theories, tests materials, and helps us set safe operational limits. Conclusion. In summary, the thin cylinder experiment teaches us how these structures handle stress, providing essential data for safe and efficient engineering design. Thank you.
My name is Bridget Clean Anakurit with matrix number CD240250. For the calculation part, the question asks to calculate hoop strain and longitudinal strain for open ends and closed ends conditions. In the open condition, there is no obstruction to the end of cylinder. Therefore, the longitudinal stress is 0 but hoop stress is equal to pressure times radius over the thickness of the wall. So we use the formula 1 over Young modulus and multiply by hoop stress to calculate hoop strain. For longitudinal strain, we use formula 1 over Young modulus multiplied by negative ratio time hoop stress. While in the closed ends condition, the force applied onto element are due to longitudinal stress and hoop stress. Therefore, we use formula 1 over Young modulus multiplied by hoop stress minus ratio times longitudinal stress. For example, we calculate hoop strain and longitudinal strain for open ends condition at 5 bar pressure. We take all the data required from the table. Then we calculate the hoop stress first and we got 7.25. After that, we calculate the hoop strain and we got 103.58 microstrain. Next, we calculate longitudinal stress and we got 3.625. Lastly, we calculate the longitudinal strain and we got negative 34.18 microstrain. Secondly, for closed ends condition at 30 bar pressure, we calculate the hoop stress first, then we got 43.5. Next, we calculate the longitudinal stress and we got 21.75. After that, we calculate the hoop strain and we got 518.89 microstrain. Lastly, we calculate the longitudinal strain and we got 105.64 microstrain.
Hello, my name is Krisma Anna Denise. So for my part, I will share the key observation from our experiment on thin cylinders. So as you can see in this slide, this is for experiment 1, open ends. So we observe a nonlinear increase in hoop stress as pressure increased. At lower pressures, some gauge, like gauge 1 at 15 units, showed negative readings. This suggests complex stress distribution due to material or experimental inconsistencies. And then the strain was higher in gauge further from the axis, particularly gauge 4 and 5, demonstrating the dominance of circumferential stress over axial stress. Importantly, the material remained within its elastic region, showing no permanent deformation, and the stress was distributed uniformly, validating thin cylinder theory. So this is for experiment 2, closed ends. With closed ends, the strain was significantly higher due to the introduction of axial stress. For instance, at 30 units of pressure, gauge 1 record 212 compared to negative 103 and 23 in the open-end setup. The combination of axial and hoop stresses led to greater deformation, with strength progressively increasing from gauge 1 to gauge 5, consistent with theoretical prediction. As in general observation, so overall, the experiments confirmed that the material behave elastically under the test pressures. They highlighted the importance of accounting for end caps in design, as they significantly alter stress and strain distribution. This result validated thin cylinder theory, emphasizing the dominance of hoop stress and the negligible effect of radial stress.
Hi, my name is Dashandra Nalaki Ramanaidu and my method number is CD240021. Now I will explain about the discussion from the lab report of thin cylinder experiment. So there is two questions. Explain the difference between the open and closed end conditions. To begin, the main difference between the two conditions lies in how the end of the cylinder are configured and the resulting stress states. An open-ended thin cylinder refers to a cylinder where one or both ends are left open. This setup allows air or particles to move freely in and out. Without any axial restraints, there is no longitudinal stress. However, due to the position effect, we still observe some longitudinal strain. On the other hand, a closed-ended thin cylinder has both ends sealed, preventing the movement of air or particles. The sealing introduces axial constraints, resulting in both longitudinal stress and op stress. This creates what we call a biaxial stress state, as two stress components act simultaneously on the cylinder walls. Second question, which case experiences a uniaxial state of stress and which case experiences a biaxial state of stress? Now let's look at the stress states of each case. The open-ended condition experiences a uniaxial state of stress. This is because the cylinder has no axial restraint, meaning there is no longitudinal stress. The only stress present is the hoop stress caused by the internal pressure. In contrast, the closed-ended condition experiences a biaxial state of stress. With both ends sealed, the cylinder is subjected to two stress of components, longitudinal stress and op stress. When we compare these two systems experimentally at a pressure of 30 bar, the difference becomes evident. The open-end system shows a no longitudinal stress, confirming its uniaxial stress state. Meanwhile, the closed-ended system exhibits both longitudinal stress and op stresses, validating its biaxial stress state. In summary, open-ended thin cylinders are unrestrained at the ends, leading to a uniaxial stress state with only op stress. Closed-ended thin cylinders have sealed end, resulting in a biaxial stress state with both op and longitudinal stresses. This comparison highlights how the cylinder's configuration significantly affect its stress behavior under the pressure. That's all. Thanks.
Hi, my name is Azamuddin Yahya and my metric number is CD240044 and I am going to talk about the conclusion of the thin cylinder experiment. So, in the conclusion, the thin cylinder has been conducted by determining the strain related to selected point on the surface of thin cylinder, and there are two types of condition, which is open end and closed end. The result obtained in a thin cylinder with open end show that the strain magnitude in all strain gauge from 1 to 5 increase as the pressure applied increase. During the experiment, the pressure reading in software SM107 is delayed compared with the mechanical pressure gauge. So we need to wait a few seconds before recording the values. Note that the higher the value of the pressure applied to the thin cylinder, the higher the value of stress and strain of the cylinder obtained. Next, there are several references that we refer when making this lab report. So that's all from me. Thank you.